Is quantum just a tech buzzword? Is it another overinflated promise from Silicon Valley, destined to fizzle out like so many other proclaimed revolutions? If you feel a deep sense of skepticism, you are not alone. For years, the conversation around quantum computing has been dense with theoretical physics and futuristic claims that sound more like science fiction than practical business strategy. We have been told it will change everything, from medicine to finance, but the proof has often felt distant and speculative. The headlines scream about breakthroughs, but for most people, the tangible results have been hard to pin down. Where is the evidence? Where are the real-world applications that go beyond a university laboratory or a press release? This essay is for the skeptics. It is an answer to the question, show me the proof. We will not dive into the arcane details of qubits and superposition. Instead, we will focus on verifiable examples happening right now, on this day, 2025, November 15th. These are not just abstract ideas. We will name the companies, describe the projects, and point to the sectors where quantum methods are already creating measurable value. The goal is to cut through the jargon and the hype to reveal a simple truth. Quantum computing, particularly when paired with artificial intelligence, is quietly moving from the realm of theory into the world of practical application. The revolution is not coming. It has already begun, one pilot project at a time. This journey will take us through 5 key industries: healthcare, finance, energy, logistics. Before we examine the proof, let's establish a clear, no-nonsense baseline. What are we actually talking about when we say quantum computing and quantum AI? Forget the complex physics lessons and spinning particle diagrams. The core concept is simple. In one sentence, quantum computing uses the strange rules of tiny physics to explore a vast number of possibilities at once. Traditional computers check one possibility at a time. It's like a key trying every lock simultaneously, instead of testing each lock one by one. That ability makes quantum machines powerful for certain problems. Classical computers are linear. They follow instructions step by step. That's why they're great at routine tasks like sending emails and running spreadsheets. But some problems have so many variables that even the fastest supercomputer would take thousands of years. These are optimization problems. These are simulation problems. These are complex sampling problems. They appear everywhere, for example when designing a new drug molecule, or when planning the most efficient delivery routes for a truck fleet. That's the sweet spot for quantum computing. So where does quantum AI fit? It's the fusion of this new hardware with smart learning algorithms. AI is about teaching computers to find patterns, make predictions, and learn from data. Pair that AI with a quantum engine, and you get a superpowered learner. Quantum AI can sift immense, complex datasets to find patterns classical AI misses. It can train models on problems once thought unsolvable. It's not a replacement. It's a specialized tool for the hardest challenges. In short, it's a faster way to navigate a maze of near-infinite choices. A new tool in our toolbox for specific critical tasks. It specializes in questions like, what is the best way to, and what is the most likely outcome if? Healthcare is one of the clearest and most compelling arenas where quantum's potential is turning into concrete progress. For decades, the process of discovering a new drug has been incredibly slow, expensive, and fraught with failure. A major bottleneck is understanding how a potential drug molecule will interact with proteins in the human body. This is a simulation problem of immense complexity. A single molecule can have a staggering number of possible configurations, and modeling its behavior accurately is beyond the reach of even our most powerful classical supercomputers. This is where quantum computing is starting to make a significant difference, offering a new way to simulate molecular interactions with unprecedented precision. Quantum hardware companies, software companies, including prominent names like IonQ, are working directly with pharmaceutical firms on this very challenge. They are using their early-stage quantum processors to model chemical reactions that are fundamental to drug discovery. By simulating how a small molecule might bind to a target protein, researchers can more accurately predict its effectiveness and potential side effects before ever synthesizing it in a lab. This doesn't eliminate the need for clinical trials, but it dramatically narrows the field of candidates, saving immense amounts of time and money. Several major pharmaceutical companies now have dedicated quantum teams and have announced pilot programs aimed at accelerating their research and development pipelines using these techniques. Beyond drug discovery, quantum AI is also showing promise in the field of medical imaging. Techniques like MRI scans, CT scans generate vast amounts of complex data. Quantum machine learning algorithms are being developed to analyze these images with a higher degree of nuance. These algorithms can be trained to detect subtle patterns or anomalies that might be missed by the human eye, or even by classical AI systems. The goal is not to replace radiologists, but to provide them with a more powerful tool for early and accurate diagnosis. Pilots are underway to test quantum-enhanced algorithms, identifying cancerous tumors at an earlier stage, predicting the progression of neurodegenerative diseases from brain scans. These applications are not happening in a vacuum. They are part of a deliberate, strategic push by the healthcare industry to embrace next-generation computational tools. The progress is incremental but steady. The initial quantum simulations are focused on smaller, simpler molecules, but as the hardware becomes more powerful, the complexity of the problems they can tackle will grow. The key takeaway is that the work has started. Real research with real budgets and real corporate partners is being done today. This is not a distant dream of future medicine. It is the practical, foundational work that is laying the groundwork for the medical breakthroughs of tomorrow. They involve real companies, from specialized quantum startups like IonQ D-Wave to established giants in banking, pharmaceuticals, manufacturing. These organizations are not investing millions of dollars based on blind faith. They are doing it because they are seeing early but promising results. The evidence is mounting. The projects are live. The world of finance runs on numbers models and the constant search for a competitive edge. It is an industry built on managing two fundamental forces: risk-reward. Every day, banks, hedge funds, investment firms grapple with enormously complex optimization problems, from building the perfect investment portfolio to pricing exotic financial derivatives. These tasks involve balancing a huge number of variables, correlations, potential future scenarios. For years, financial institutions have used powerful classical computers to run these models, but their capabilities have limits. This is precisely why Wall Street has become one of the most eager and active early adopters of quantum computing. One of the most mature applications of quantum in finance is portfolio optimization. The challenge is to select a mix of assets, stocks, bonds, commodities, that will deliver the highest possible return for a given level of risk. With thousands of available assets, the number of possible combinations is astronomical. Quantum algorithms, particularly those run on quantum annealers like the ones built by D-Wave, are naturally suited to this kind of problem. They can explore a vast landscape of potential portfolios simultaneously to find optimal or near-optimal solutions much more efficiently than many classical methods. Major banks like JP Morgan Chase and Goldman Sachs have publicly discussed their research and pilot programs in this area, signaling a serious commitment. Another critical area is risk modeling. Financial institutions must constantly assess their exposure to market fluctuations, credit defaults, other economic shocks. This often involves running complex Monte Carlo simulations, which are computationally intensive and time-consuming. Quantum algorithms promise to speed up these simulations significantly, allowing firms to run more scenarios in a shorter amount of time and get a more accurate picture of their risk profile. This enables better-informed decisions, especially during times of market volatility. Several financial services companies are now collaborating with quantum startups to develop and test quantum-powered risk models, aiming to gain a crucial advantage in a fast-moving market. The results from these early pilots are not always about a dramatic, overnight replacement of existing systems. Instead, the gains are often seen in hybrid quantum classical approaches. In these setups, the quantum computer tackles the part of the problem it is best at: complex optimization sampling, while classical computers handle the rest. Even a small improvement in speed or accuracy can translate into millions of dollars in a financial context. The fact that these notoriously cautious and bottom-line focused institutions are investing resources and forming dedicated quantum teams, the global push for a sustainable future hinges on breakthroughs in energy technology. We need better batteries to power electric vehicles, more efficient ways to manage our power grids, new materials to capture carbon from the atmosphere. These challenges often come down to chemistry and complex systems optimization problems quantum computing can uniquely tackle. Energy and materials science are now fertile ground for real-world quantum applications, moving from theory to pilot projects with major industry players. Next-generation batteries are a prime example. Battery performance depends on chemical reactions inside. To make batteries that are lighter, hold more charge, and last longer, scientists need new materials for electrodes and electrolytes. Simulating quantum behavior of those materials stumps classical computers. Quantum computers can model these molecular interactions directly. Automotive companies, chemical companies, are partnering with quantum firms to simulate battery chemistries. That lets them vet materials, virtually cutting time and cost of lab experiments. Quantum optimization is also being applied to energy grids. Modern grids are more complex as intermittent renewables like solar power and wind power are integrated. Operators must balance supply and demand in real time to prevent blackouts, minimize costs, and reduce carbon emissions. Utilities are testing quantum-inspired algorithms to optimize energy flow across the grid, decide which power plants to activate, and manage energy storage better. These pilots aim to build a more resilient, more efficient, and greener power infrastructure. Industrial processes are another frontier. Fertilizer production via the Haber-Bosch process is extremely energy-intensive and uses a large share of global energy. The reaction relies on a catalyst. A better one could cut huge emissions. Quantum computers are simulating candidate catalysts that might enable the reaction at lower temperatures, lower pressures. Every product we use, from the coffee we drink in the morning to the car we drive, is the result of a fantastically complex supply chain. Getting the right parts to the right factory at the right time, then routing the finished product to a warehouse, and finally to a customer's doorstep involves a mind-boggling number of interconnected decisions. This is the domain of logistics and manufacturing, an area filled with notoriously difficult optimization problems. For decades, companies have used classical software to manage these traveling salesmen and scheduling puzzles, but the solutions are often just good enough. Quantum computing offers a path to truly optimal answers, promising massive savings in cost, time, and resources. One of the most direct applications is in vehicle routing. For a company like UPS or FedEx, figuring out the most efficient routes for its entire fleet of delivery trucks is a daily challenge with millions of variables. A small improvement of just 1% can translate into enormous savings in fuel and driver hours. Quantum-inspired optimization algorithms are now being tested by logistics companies to solve these vehicle routing problems. By exploring a much larger solution space than classical methods, these algorithms can identify shorter, more efficient routes that reduce travel time and fuel consumption. The same logic applies to airlines optimizing flight paths and shipping companies planning cargo routes. In manufacturing, the challenge is often one of scheduling. On a factory floor, a complex series of tasks must be performed on a limited number of machines, each with its own constraints. Efficiently scheduling this job shop workflow is critical to maximizing output and minimizing downtime. A poorly optimized schedule can lead to bottlenecks, delays, and wasted capacity. Quantum and quantum-inspired solvers are being used in pilots to tackle these scheduling problems, helping manufacturers create more fluid and efficient production lines. Companies in the aerospace and automotive sectors, where assembly is incredibly complex, are among the early explorers of this technology. The impact extends across the entire supply chain. From optimizing where to store inventory in a massive warehouse to deciding how to load cargo containers for perfect balance and space utilization, quantum's ability to handle complex, multivariable problems is finding a home. The results are tangible and easy to measure. Reduced fuel costs, faster delivery times, less wasted warehouse space. The reach of quantum computing is extending into some unexpected, yet vital corners of our world, including agriculture and digital security. These fields might seem worlds apart, but both face complex challenges well suited to quantum solutions. In agriculture, the challenge is optimizing a biological system with countless variables, weather, soil chemistry. In security, the challenge is creating a defense against a future threat, the power of a quantum computer. Pilot programs and early-stage applications are already showing quantum's broad impact, touching the food we eat and the data we protect. In agriculture, a key goal is increasing crop yields while minimizing resources like water and fertilizer. This is an optimization problem on a massive scale. Quantum AI models are being tested to analyze a wide array of data: weather forecasts, soil sensor readings, satellite imagery, historical yield data, to give farmers better predictions and recommendations. For example, a quantum-enhanced model could set the optimal planting schedule or calculate the precise fertilizer amount for a field section. Still experimental, startups and ag-tech firms are exploring these tools to bring precision farming and help global food security. At the other end is quantum cryptography, a technology addressing digital vulnerabilities. Today's encryption protects bank transactions and state secrets, but relies on math too hard for classical computers. A mature quantum computer could break that encryption. To counter that, researchers developed quantum key distribution, QKD. QKD uses quantum physics to create and share encryption keys that are provably secure. Any eavesdropping disturbs the system and alerts users. This is not science fiction. QKD is already in pilot programs with governments, financial institutions, and telecommunications companies. They are building quantum-safe communication networks now, long before a threatening quantum computer arrives. It's a proactive, practical use of quantum principles. For any skeptic, the most important question is, where is the proof? The most compelling evidence that quantum computing has moved beyond hype lies in the growing number of public announcements, partnerships, pilot programs. This is not happening behind closed doors anymore. We are in an era of transparent experimentation. Major corporations are openly collaborating with hardware providers, software providers, and the results are starting to be shared. The proof is not a single breakthrough. It's the steady accumulation of real-world projects. Consider the timelines. As of late 2025, we are well past pure academic research. Over the last 3 to 4 years, there's been a marked shift. IonQ, D-Wave, Rigetti, others. These companies have published roadmaps and largely hit milestones building more powerful, stable processors. Their press releases are no longer just about hardware advances. They're filled with partnerships with Fortune 500 companies. Bank pilot, repricing derivatives. Pharma collaboration, drug candidate screening. Auto project, better battery design. These projects are not for show. BMW, Goldman Sachs. Airbus, AbbVie. They do not assign big budgets and top engineers without a clear business case. They're investing because quantum approaches, often hybrid with classical computers, are beginning to outperform existing methods on narrow problems. The gains might be a 10% speed up in a complex simulation or a 5% improvement in an optimization. That may not sound revolutionary, but in industries where a single percent can mean hundreds of millions, it's enough to justify investment. The evidence is verifiable. So, if quantum is real and the pilots are underway, what comes next? The journey ahead is not about flipping a switch and having quantum computers suddenly run the world. The future is more nuanced and practical. The next several years will be defined by 3 key trends: scaling the hardware, perfecting the hybrid quantum classical model, expanding the application of quantum AI to new and even more complex problems. We are currently in a phase of transition, moving from demonstrating quantum advantage on niche problems to integrating quantum solutions into mainstream industrial workflows. This is the critical stage where the technology proves its long-term value. First, the focus will be on scaling. Quantum hardware providers are in a race to build machines with more qubits, lower error rates, and longer coherence times. As the machines become more powerful, the complexity of the problems they can solve will increase exponentially. Small molecule simulations, large protein simulations, routing optimization for a small fleet of vehicles manage the entire global logistics network of a multinational corporation. This hardware progression is the engine that will drive the expansion of quantum's impact, unlocking more and more challenging use cases across all industries. Second, the hybrid model will remain the dominant approach for the foreseeable future. It is a mistake to think of quantum and classical computers as competitors. They are collaborators. Most complex problems have parts that are best suited for classical machines, and other, specific parts that are perfect for a quantum processor. The art and science of the next decade will be in perfecting this interplay. Software platforms are being built to seamlessly break down a problem, send the hard optimization or simulation part to a quantum computer via the cloud, and then integrate the result back into the classical workflow. This pragmatic approach delivers value now, without having to wait for a perfect, fault-tolerant quantum computer. Finally, we can expect to see quantum AI applied to some of humanity's biggest challenges, particularly climate change. Simulating climate chemistry to discover new catalysts for carbon capture, designing more efficient solar cells, creating a truly intelligent, responsive global energy grid. As the hardware and algorithms mature, we will see a concerted effort to point this new computational power at creating a more sustainable world. What comes next is not a sudden revolution, but a steady, deliberate, and powerful integration of a new tool into our problem-solving arsenal, with the potential for profound impact. If you think quantum is still in the lab, think again. These aren't theoretical studies. They're active pilots with measurable results, global rollouts, and big names involved. Still skeptical? Links to all the evidence are below. See for yourself. Share your thoughts. What industry do you think quantum will disrupt next? The time to start paying serious attention to its real-world impact is now. Let us look at the facts. These aren't hypotheticals. The projects are live. The timelines are being published. While it is crucial to maintain a healthy dose of realism, quantum is not a magic bullet for every problem, it is equally important to acknowledge the shift that is underway. The era of dismissing quantum as a far-off fantasy is over. Let's keep it real and keep it verified. Enjoyed this? Like, subscribe, and share for more new videos weekly.